Hello and welcome to the 7th in a series of videos aimed at developing retro games in vanilla JavaScript, using the canvas element. My name is Anthony, and please join me in my corner of the web, where I like to build stuff in the browser with the latest technologies. There's not going to be much of an intro in today's video unfortunately, as I'd like to continue pretty much from where we finished in the last video. I will mention that we'll look into mostly finishing up the code that I originally planned in the previous video, but decided to split it out into this one due to time. Although towards the end of the last video I did mention we still have to complete a few of the final states for the general behaviours the fighters have. These are basically transitional states, which while minor in the grand scheme of things, helps us to stay the feeling of the original arcade game and to replicate it more closely. In regards to what we'll be looking to complete in this video, let's refer back to our dreaded to-do list once more and see what we have remaining. As you can see, we still have a mountain to climb, but hopefully this will start to change over the next few parts of the series, as we start to implement some of the more core game mechanics. In this video, however, we'll be attempting to add a little polish to our jumps with a couple of transition states. Then we'll finally add the ability for the fighters to change direction and actually face each other, which is obviously needed in a fighting game. This leads on to the turn states, which again are another set of transition states that polish up the direction changes the fighters make. And finally, we'll move on to the main subject of today's video, collision boxes. As you'll soon come to realise, Street Fighter has many different types of collision boxes, so we'll first explain what these actually are, and then go ahead and start to add our first set of these, called push boxes. We'll then understand why these are actually crucial and help us with our turn states. And before we jump into the video, I'd like to say thank you for the support so far. It's been great to see the new subscribers, likes and your comments on the current videos. Although, if you're new to this channel and you'd like to see more of this deep dive content, why not code along with me and click the subscribe button? This would help me greatly in this whole YouTube ecosystem we have. Okay, let's get back into it. So picking up where we left off in the previous video, we finally had our fighters fully controllable from input devices such as keyboard and gamepads. However, one thing I did mention in that video though, was that we had a slight issue with the jump state. At the moment, we're unable to jump diagonally from either a vertical jump or from the idle state. I'll now admit, this was on purpose as I'd like to add a couple of new states to fix this, but unfortunately couldn't add it in the last video due to time. If we were to check the original game, you'll notice whenever a fighter transitions from and to a jump, they bend their knees, just like in real life I guess. This happens for a number of frames and makes them vulnerable to attacks, but for our code, we're missing these frames, or rather states. In regards to the state before the jump, this is an opening to allow the user to choose which direction to jump in, which will fix our current issue. Let's look to add these missing states to our state machine. First things first, we'll need to add the two new properties to the fighter state enum object. We'll name them jump start and jump land, and add them alongside the other jump properties. If you can think of better names to call them, then go ahead. Unfortunately my brain is coming up empty at the moment. Next we'll need to add the new frame and animation data to the Ken and Ryu classes, which again I've already prepared before the video, so we'll just copy them over. As both of these states are only transitional states, notice how it only has one sprite and the animation has a -2 for the last frame's frame delay, to acknowledge that this animation does not loop. For now we'll ignore the jump land state with its strange animation and come back to it later, as we'll be concentrating on the jump start state first. Now back in the fighter class, let's look to set up the state machine and the necessary properties and functions. We'll first add the handle jump start init and handle jump start state stub functions, and then add the new object to the state's property for this state, adding the new functions we just created as references to the init and update properties. I actually find it easier to pick the functions from the VS Codes dropdown if we have the stubs available first, rather than typing the names out twice. While we're here, we'll next add the required states to the valid from array too. We'll do the same for the other jump states and replace any reference to the idle state and change it over to the jump start state instead. We can safely remove the walk states now also, as we know we'll want the jump start state to initiate all jumps moving forward. Back in the start init function, we'll just call the idle state function again, as we'll be wanting to reset the velocities coming from the walk states. In regards to the start state function, we'll initially wait until the animation has completed, then if it has, check the necessary direction on the controls. Based on which direction is held down, we'll transition to the correct jump state. If this is neither forward or backwards, we'll default to jumping up. The last thing we'll want to do for this new state is update the idle and walk state functions and replace any reference to a jump state over to the jump start state instead, as again we'll want the jump start state to initiate the correct jump state moving forward. Let's quickly now check to see if we have this working correctly. We can see that Ryu now briefly bends his knees before jumping, which mirrors what the original game does. and we can also finally jump diagonally from the idle state too, which is great. Although if we compare to what we have in the original game, we're still missing the state when he lands. So let's look to add the jump land state next. Back to the code in the state machine, we'll add another new object for the jump land state, again adding the new references for the init and state functions. As the state is for when the fighter lands after the jump is completed, we'll only add the jump states to the valid from array. In the handle jump land init function, we'll again just call the handle idle init function to reset the velocities. As for the handle jump land state function, we're going to do something a little bit different. If you remember, the animation for this state was a little strange, as it had 2 frames with the same key, but with 2 separate frame delays. This was designed this way to replicate how the original game handles its land state. We want the fighter to always wait for the full length of the first frame, but as for the second frame, this will only happen if the player does not touch their controls when they land. You can see what I mean in these clips taken from the original game. On the left hand side of the screen, as Ryu comes down from the jump, if you hold down the up direction, notice how he briefly holds his knees bent, but then springs straight back into the jump again, whereas on the right side of the screen, if you were to leave the controls alone, he bends his knees for a little longer before the game resets his state back to the idle state. This is why we've done the animation a little differently, to allow us to separate these behaviours and delays. So in the handle jump land state function, we'll just return out of the function early until the animation frame is beyond the first frame, as we know we want the fighter to display the land frame for the length of this frame regardless of what happens next. However, if the animation is in the second frame, we need some special logic to handle this state's unique behaviour. So next, in the input handler module, we'll first add a new helper function called isIdle, which will check each direction of the control and return false if any direction is currently held down, and only return true if none are held down. Back in the handle jump land state function, we'll now call this new isIdle function and see if it returns false, meaning the player is holding a direction after the first frame. If so, we'll call and refer back to the handle idle state function instead, as that ultimately has everything we need in regards to valid states from the jump land state, so it seems pointless repeating the same code here. If they aren't holding the direction, we'll wait until the animation is fully completed before returning back to the idle state. Just like the previous state, we'll now have to go back to the previous code and correct any state changes and valid from entries. Starting with the handle jump state function, changing the idle state to the jump land state when the fighter's Y position goes past the stage floor. Next, in the state machine, we'll need to ensure we add the jump land state to the jump start and idle states valid from arrays. And that should be it. So let's again have a quick check against the original game. And it seems we have it working as intended. As Ryu lands from a jump, if the player leaves the controls alone, he waits a little longer before transitioning over to the idle state. But if the player holds the up direction down, he jumps straight back into another jump. Great stuff. Okay, at the moment both Ken and Ryu are stuck in their initial directions, either facing right or left, which looks a little odd when they have their backs against each other. If we want to actually have them be able to fight each other, really we want them to facing each other too. So let's see how we can do that next. The first thing we'll need is a reference to the other fighter, so that we can check their position against ours. So I'm going to add a new local class property and call it opponent. Next, within the Street Fighter game class, I'm going to simply use the fighter's array and set the opponent's property to the opposite fighter from that array. This is just temporary for now, as we'll look to refactor this once we start to build up our game state, which will come in a future video. Then, back in the fighter class, we'll add a new helper function and call it getDirection. For now, this will compare the fighter's X position and return the correct direction based on whether the opponent's X position is lower or greater than ours. Then, in the main update function, we'll set the direction based on the result of this function. And as the first pass, that's all we need. Let's check the result in the browser. As we can see, the fighters now flip and change direction as they pass each other. So far so good. However, when you jump over the opponent, the code gets confused and constantly changes direction of the fighter until they land. This is due to how the forward and backwards jump states are handled differently. Okay, we can easily fix this by applying a conditional check to the direction assignment. We'll ensure that you only change direction if the fighter is on the ground, by using the idle and walk states. Back in the browser, we can see this now fixes the issues for when we jump over the opposite fighter. Although if again we were to compare this to the original game, you'll notice the fighters have a separate turn animation for when they flip direction, both while standing and while crouching. Also, when the fighters land from a jump, they also perform a turn animation, something we've yet to add in our code. So before we move on, let's now add these new states to our state machine to round off this set of basic moves. We'll again follow the usual method of setting up new states. First adding the new entries to the fighter state enum object, called idle turn and crouch turn. Then adding the necessary animation frames and animation arrays to both the Ken and Ryu classes, which I'll pull from my stash once more. Both of these new animations have 3 frames and again end with a -2 frame delay to ensure that they are transitional animations that do not loop. Next, in the fighter class, we'll add 2 new stub functions and call them handle idle turn state and handle crouch turn state. Then in the state machine, we'll add the necessary idle turn and crouch turn objects too, again updating the init and update properties to match our new stub functions. Not forgetting to update the valid from states for each. Lastly, we'll also add the idle turn state to the valid from property to the idle state, and the crouch turn state to the valid from property for the crouch state, as these are naturally the only states they can transition to. Now back in the state functions we created, both of these functions are going to be similar in that they simply wait for the turn animation to finish, and then transition back to their natural state, either idle or crouch. Although, we'll make a call to the main state function as we want to interrupt the turn animation if the player performs an action, such as jump or an attack. Notice how we're again turning out of the function early if the animation has not completed. In fact, we should probably extract this line out to a helper function for readability purposes, as we're using this in a few functions now. Let's do that at the end of the video, as we'll now need to update our directional logic to work with the new turn states. At the moment, we're adding our directional change logic to the main update function, and checking if we're on the ground using a lookup list of valid states. Rather than having this lookup list, let's perform the check within each of the valid state functions instead, again to remove any incorrect behaviours. So let's remove this current code and start updating the idle state first. Here, however, we're looking to incorporate the turn state and its animation to replicate the original game. So we'll create a new variable called newDirection and assign the result to the getDirection call to that instead, and then compare the result of this variable to the direction property. If we should be facing a different direction, we'll only then set the direction and therefore change the fighter's state to the new idle turn state, performing its turn animation. For both walk state functions, we know from the original game that these are instant directional changes, so we can simply assign the correct direction to the directional property in both of these functions. For the crouch state, this is very much the same as the idle state. The only difference here is that we'll obviously use the crouch turn state instead as the transition. And lastly, for the jump land state, this requires something a little different due to its complex transitions we set up earlier. Looking at the previous states we set up, we've established that if the player is idle, we'll transition to one of the turn states, but if they are not, we want to instantly change the direction, so we'll need to use both of these code paths within the state function. We'll start by setting up a temporary variable called newState and assign it to the idle state, this being the default transition state. We'll update the change state call to now use this variable instead. Then below this idle conditional check, where we know the player is moving the controls and therefore not idle, we'll set the direction property to the getDirection function. Whereas below this, we know the player is definitely idle, so we'll use the same logic we used in the idle and crouch states, creating a temporary new direction variable and then comparing the result to the direction property. This time we'll set the new state variable instead of calling the change state function directly, as we know we have one at the end of the function. Lastly, we'll then move the animation complete check into the else block as a catch-all to ensure we don't change state until the animation is complete. In summary, the fighter will change state and direction instantly if they are not idle, but if they are, they'll change state to either the idle or idle turn state depending if they need to change direction or not. And with that, we should be able to see the result in the browser. We'll again compare with the original game, and as you can see, we're now replicating the turn states and animation as we jump over the fighter. This works just the same for when they're standing or crouching too, which again is great to see, as this proves we're very much along the lines of the original game. However, we still have an issue as you can see. The turn states now get confused when you attempt to walk past the opposite fighter, and again, go into a constant loop of flipping back and forth like we had before. This time, instead of trying to code around this, let's investigate how the original game handles this. It seems they don't allow for this at all. Instead, it ensures the fighters never get in this situation by applying a collision check when they bump into each other. When they do collide, the game seems to adjust the fighter's position instead, preventing them from ever overlapping. Depending on the position and the state of the fighters will either get pushed or forced to the front or the back of the other fighter. Most games handle these type of collisions by applying boxes around the player's main fighter sprite, and Street Fighter is no different. More recent games may apply more complex shapes, but for games of this era, rectangular boxes were common practice. Reason being, boxes are the simplest and quickest form of collision detection. Usually these boxes are never visible to the user, and are handled within the game code based on a predefined area. but we'll magically turn them on so you can see how it works. Notice how each fighter now has a green box that covers the general area of their sprite and follows them around. Well, this is the collision box and is usually called the push box. These boxes are applied to each animation frame, and it's this box that causes this special type of behaviour. As it's applied to each frame, it can be moved or resized as required for the animation, helping it to cover the correct area occupied by the sprite. We'll be digging a little deeper into collision boxes over the next parts of the video series, as fighters have multiple sources and types of these, which includes the push, hit, hurt and even throw boxes. So rather than getting overwhelmed with all the different types right now, we'll focus just on the push boxes today. So back in the code, we'll now need to apply the correct collision box data to all the individual frames, which means extending our entries within the frames map object for both the Ken and Ryu classes. But before we do this, it should be noted that even though the push boxes can have unique dimensions per frame, they actually only have a limited set of known defined areas. So the first thing we'll do is create a lookup object to store these, and refer back to those instead, for ease and readability purposes. In the fighter constant file, let's add a new const object and call it pushbox. We'll add 4 properties and call them idle, jump, bend and crouch. Each of these will load an array for their value containing 4 numbers. The first 2 values are the X and Y offset positions, based on the current animation frame's origin point, while the last 2 values are the width and height of the pushbox. The names behind the keys are pretty self-explanatory, but do not worry if not, as we'll come back to these in a moment. With this lookup object set up, we can now go back to our Ken and Ryu classes and extend each entry in our frame's map object with one of the keys, applying the necessary pushbox dimensions to that specific frame. You'll notice how the key names seem to mirror the frames and their state somewhat, and is why I mentioned they were self-explanatory, although the bend key is the only really unique one for now, as that's used for the middle frame within the crouch down animation. Honestly, I couldn't think of a better name at the time. You're probably seeing a trend here, so if you can think of one, please by all means change the key name. Also, why not drop it in the comments section, as I'm interested to hear your alternatives. Either way, the same pushbox keys were assigned to each frame in the Ken class also apply to the Ryu class, so it's just a matter of copying them over. I should also mention that I've now wrapped another array around the values to keep the pushbox values separate from the frame data and origin points. This alters the structure of the frame map data, so we'll need to make some small adjustments to any code that uses it in the fighter class. Okay, with that acknowledgement and with the new data in place, let's jump over to the fighter class and make the necessary changes. So before we continue, we'll update the draw function to accommodate the new frame structure. We'll add a further square bracket around the destructured values from the get function. Next, we'll add a new class property called pushbox. This will be an object that will store the current frame's pushbox, funnily enough. Let's give it a default value with an X, Y, width and height properties that are all set to 0. As we'll be using the pushbox in a number of places moving forward, we'll create a new helper function called getPushbox, which will take a frame key as a parameter. This will be used to deconstruct the pushbox values from the frame's map object and return the same structured object as our new class pushbox property. We'll also give it a default array value of 4 zeros to ensure we don't get an undefined value. Moving down to the update animation function, we'll first deconstruct the frame key from the animation array, and then after the animation frame increment, we'll call the new getPushbox function and set the result to the new pushbox class property, meaning every time we update the animation frame property, we'll now also set the pushbox property too, using the same frame key. Now that we have everything set up, we'll extend our debugging function, which currently only houses our origin point to draw the pushboxes to the screen. This will make it much easier to visualize the collision code we're about to set up. Let's first deconstruct the frame key from the current animation and use that to call the new getPushbox function. We'll assign the result to a local variable called pushbox. With this, we'll go ahead and proceed to draw a rectangle using the necessary context functions above the origin point code, as we'll want to draw this first. Just like the origin point code though, we'll need to start with the begin path function to ensure we clean out any previous context paths. Then we'll set up the style colours for both the stroke and fill operations. I'm using green for both values, but using a transparent fill style using an extended hex value. Now we'll use the fillRect function to draw a fill rectangle using the fighter's position and offset it using the pushbox values. As previously mentioned, due to the strange way the context draws its pixels, and just like the origin point drawing calls below, we'll need to add a 0.5 to the X and Y positions, otherwise the drawing functions will look blurred. Remembering we'll also have to use the math.floor function with any decimal values to remove any anti-aliasing too. Then we'll use the rect function to draw the same rectangle, but this time for the outline. So we'll copy the previous dimensions over to this call's arguments. And finally, we'll apply the draw calls to the stroke function. While we're here, we'll also fix up the cursor drawing a little too, as I'm not happy with what we did previously. I'll remove the decimal value from the X position on the first move to and line 2 calls, rounding the line 2 value to 5, and do the same on the Y position on the second set of functions, but this time rounding up the move to value to 5 instead. Lastly, we'll change the 0.5 to an addition rather than a subtraction here too. Okay, let's see what we have in the browser. Just like the original game, we now have a green rectangle drawn over our fighter's sprites, clearly showing where our fighter's push box is. As a bonus, our origin point looks much clearer too. As mentioned, this will definitely help us visualize the collision checks. Before we can do that though, let's update our code to work with the push boxes. Back in the getDirection function, we'll update this to include the push box rather than just using the position alone. We'll simply ensure the width of the push box has completely past the opponent, before allowing them to change direction. This logic seems to be how the original game changes direction, so hey, why shouldn't we replicate it too? Next, within the update stage constraints function, we'll do something similar with the screen constraints. Now that we have an actual width dimension for the fighter, it makes sense to replace the temporary width const value we're currently using with the push box. We'll quickly do that, removing the const value and replacing it with a push box width instead. With those changes in place, let's have another quick look in the browser. Now that we're using the push box for the directional change, this has fixed our overlapping issue, in that we can now walk through the opponent with no adverse effects. The fighters are also constrained by the size of the screen now, using the push box too. Compared to the original game, we can see we're also replicating when the turn animation is instantiated. All steps in the right direction it seems. Okay, the next step now is to actually apply some collision checks to prevent the fighters from ever overlapping in the first place. Let's add a little helper function that checks for overlapping rectangles. Over in the Explorer window, we'll add a new folder in the source folder and call it utils. Inside that, we'll create a new file called collisions.js. This file will be used to house any utility functions that will help with collisions moving forward. But for now, let's add a new function which I'll call rexOverlap. This function will take 2 sets of rectangular dimensions as parameters. I've added a number 1 to the first set and a number 2 to the second, to identify which is which. Inside this function, we're simply checking if these dimensions overlap by comparing the furthest points of the rectangles, based on their X and Y position. Back in the fighter class, let's now add a local helper function called asCollidedWithOpponent, which we'll use to compare the current fighter's push box with the opponent's. We'll use the new rexOverlap function and pass in the necessary position and push box dimensions. As you can guess, this should return true if the fighter's push boxes overlap, and false if not. Okay, now that we have a way of checking that our fighters have collided, let's apply that to some logic that will adjust the positions of the fighters so that they don't overlap. As this will be a constraint on the fighter's movement, we'll add it to the update stage constraints function. So under the current code, let's add a new condition with the new hasCollidedWithOpponent function. Here we'll add 2 further conditions based on the fighter's current X position. First, if it's lower than the opponent's X position, and second, if they are greater than the opponent's X position. As we'll be adjusting the fighter's X position, we need to ensure that we don't move them outside of the screen dimensions too. So in the first condition, we'll constrain the value with a mathMax function, and in the second function, we'll use a mathMin function. This is to ensure we always have a cap on the value we're assigning to the X position. Inside the mathMax function, as the fighter is coming from the left hand side and therefore has a lower X position than the opponent, we'll adjust the fighter so that they are always in front of their push box. We'll do this by using the push box width, subtracting it from the X position, assuring it is adjacent to the opponent's push box X position. Along the same lines, we'll do something similar for the opposite side. As the fighter is coming in from the right hand side, and therefore has a greater X position than the opponent, we'll adjust the fighter so that they are always behind their push box. This time though, taking into account their push box width, and adding it to the X position, ensuring it's adjacent to their push box width position. And finally, the values within the math functions are the lowest and highest constraint values we expect the fighters to live within. We're using a min value of the push box width and a max value of the canvas width. As mentioned, this will cap the fighter's X position so that they stay within the limits of the screen. So with that complete, let's have another look in the browser and check to see how this works out. Excellent, we're unable to pass through the opponent fighter, which prevents any overlapping issues and actually gives them more substance, producing a feeling that they now exist in the game. As per usual though, we're still missing something. If we were again to compare to the original game, notice how we're able to push the opponent if they're idle. In our version, the opponent is a rock and doesn't budge. Not to worry, let's quickly add this behaviour to our code too. Back to our collision code then, inside the X position checks, we'll add another conditional check based on the current state of the opponent. If they are idle, crouching or jumping, we'll simply adjust their X position a little to account for the push effect. However, if we're applying a velocity to the X position, we'll also need a time object, which we currently don't have. So in the update function, let's add this to the update stage constraints function. To follow the same formatting of the parameters, we'll make it the first one. Then, back in the conditional check, we'll now multiply the value of 66 to the time.seconds passed value that comes from the main game loop. We'll copy this to the other X position check below, but this time subtract the value from the opponent's X position. And hopefully that should be it. Let's quickly check again in the browser. Hopefully you'll agree, this looks like we're in a good place. If you push up against the opponent, they'll ever so slowly be pushed in the opposite direction, which again seems to replicate the behaviour of the original arcade game. The last thing I'd like to add is another small transition behaviour. While not a complete new state, it's something we're missing. When you hold down on the control, you naturally perform a crouch, but if you let go of the control before the animation has completed, at the moment the animation will continue to the end before the fighter will spring back up to the idle position. Unfortunately, that doesn't seem to be how the original game works. As you can see here, the fighter will automatically transition to the crouch up state, completely skipping the crouch state. Okay, for completeness, let's go ahead and apply some code to replicate this behaviour too. In the handle crouch down state function, we'll use the isDown function on the control to see if it's no longer held down. If not, we're going to break the norm for now and set the current state directly, as this is very unique behaviour. We'll set it to the crouch up state and adjust the animation frame so that it mirrors the current frame of the crouch down state. We'll come back to this in a later video. But if we were to check the browser again and compare it with the original game, everything looks good. And we now finally have a complete set of basic moves and transitions that pretty much replicates the arcade game. This puts us in a perfect position to now move on to the attacking and defensive moves in the upcoming videos. So before we finish the video, there's a number of things I'd like to clean up and refactor. Starting with a little typo I found on the update stage constraints function. It seems to be missing an S in its name somehow. So let's quickly change that and update the only reference in the update function. Easy win. Next we'll add a couple of helper functions. The first one for resetting the velocities I mentioned in the previous video. I'm going to create a stub function and call it reset velocities. Then I'll move the code from the handle idle state function over to it, and then call this function within that one. We'll also update any references to the idle function over to this new function instead. So the next helper function is the one I mentioned earlier in the video, and it'll be used to check if an animation has completed or not. We'll first find a line of code that checks for this, using the -2 frame delay, and copy it. Then next to our previous helper functions, we'll create a new arrow function called isAnimationCompleted, and paste this line as the return value. And again we'll update any of these lines and call this function instead, which I think you'll agree makes our code much easier to read. The next refactor we'll perform also relates to the animation in fact. One of the rules I like to keep by is to remove any magic numbers within our code. And funny enough, in our new isAnimationCompleted function, and actually throughout the animation arrays, we're doing just that, using -2 and zeros to present different behaviours for the animation. So I'm going to create another enum object within our fighter constant file and call it frame delay. This will have two properties called freeze and transition, presenting the special end frame delays of our animations. Now within both our Ken and Ryu classes, I'm going to replace any instances of either 0 or -2 as the final frame delay and replace it with the new enum object value. Again, hopefully making our code more easier to read. Once we've updated the first class, we can simply copy the whole animations block over to the other class, as the animations are exactly the same for both Ken and Ryu, making the move a little easier. We'll obviously now need to do the same within our fighter class too. Thankfully though, there's only two places where we need to update the code. The first is at the end of the new isAnimationCompleted function, changing the -2 over to the transition value, and the second is in the update animation function, where we'll replace the 0 check with the freeze value. In fact, now that we've migrated all the instances over, from this point on I'm going to change the transition value to a -1 instead of a -2, just to keep the numbers in sequence. Keeping with the remove all magic numbers theme, I'm going to add another constant value within our fighter constant file, called push friction. This is to replace the push speed value of 66 we've just previously added. So we'll jump back into the now correctly spelled update stage constraints function and replace the 66 values with this new constant value. Another quick and easy win. While still in the fighter class, the next refactor is within the idle state and walk state functions. Instead of having individual if statements for the control checks, we'll consolidate them into an else if block, making the checks a waterfall condition, which prevents the problem of players pressing two directions at the same time, and could potentially speed up our code a little in certain scenarios. The last change I want to do is to correct the timing, velocities and animations with both the Ken and Ryu classes. I've attempted to validate these values with the actual game, and it seems a few of them are a little off. That said, I was also actually surprised with how close my guesstimates were with some of them too. As with all these type of changes, I have the values stored elsewhere, so let's just copy them over rather than typing them out again. Starting with the initial velocity object. You'll notice I'm using a special calculations for the values now, but this is just a fancy way to say I'm counting the frames in the original game and dividing them by 60, which we know is the FPS the original game ran at. Next, I'm going to copy the new animation timings and framings over too. Please pause the video if you need to see the new values. Although again, you'll notice the frame delays are now in multiples of 16.6, which is the time per frame based on the original FPS. Once done though, we can again just copy the same values across the other class, as both the Ken and Ryu classes have the same timings and animations. Okay, let's do one more in preparation for the next video. We'll move the FPS counter out of the status bar HUD area and move it to the bottom right hand corner of the screen. So in the FPS counter class, we'll decrease the font size to 14 pixels, set the fill style to green so that it stands out a little more on the background, and then justify the text to the right hand side. Lastly, we'll change the X and Y positions so that it's 2 pixels from the width and height of the canvas dimensions. We'll no longer need the FPS text either, so let's go ahead and remove that too while we're here. And with all those changes and refactoring complete, let's do a final test in the browser to ensure we've not broken anything. And hopefully, yours is just like mine and working just fine. The fighters should now be moving and animating more like the original game than ever before, which again is great to see. And to top it off, the FPS counter is also correctly displayed in the bottom right hand corner too. We've now got a stable platform in preparation for adding the attacking moves and adding a proper stage background. So in summary, let's review what we've completed today. We've done some heavy refactoring in this video, so hopefully you're all okay with us making those changes as we go. I like to keep my code clean and easy to read where possible, so refactoring is a big part of that. I know some people like to design their code up front, but personally I prefer to do it after I have the code working, as I find it easier that way. At this point though, we now have a complete set of standard moves. As previously mentioned, the next step is now to extend our collision boxes to add the hit and hurt boxes, and therefore the attacking and defensive moves, which I guess is what everyone is waiting for. Although we'll have one more video before that, as we'll need to get the status bar or HUD in first. And while we're at it, we'll also add a proper stage background too. So this will be the subject of the next video, just to give us a little break from the fighter states, just for a little while at least. This means having a camera system to allow the background to scroll. This will include adding parallax scrolling and animating the sprites in the background too. If we get time, we'll also add the 3D effect on the floor. Either way, we'll also get the full health bars and time countdown in too, along with all the other stuff that goes with it, like the score and the battle win icons, etc. So yeah, this means we'll have some new things to code and play with. Also, apologies for the lateness of this video. As mentioned in the vlog update, this was necessary so I could focus on moving the code forward and hopefully getting ahead of the next couple of videos. I'll no doubt need to do this again at some point unfortunately, as we start to move on to the more complex game mechanics. I'd personally like to have the code somewhat planned out before going ahead into making the videos, unless you'd prefer all my experience to be visible in the videos themselves. Anyway, enough of the chatter, let's look at closing the video. Again, if you've got this far, I'd again like to give you a big thank you. It's really appreciated, you're the special ones. And for all the newcomers, thank you too for the recent likes, subscribes and comments on the video series. It's been nothing but a welcome surprise. If nothing more, hopefully I'm doing something right here and you're finding this content somewhat useful. So with that, I'll say my goodbyes and hopefully see you in the next one. And out.